All right, everybody. So welcome back. We're going to take a look here at Kirchhoff's laws, and we're just going to work through a few example problems just to kind of see how they apply to different types of circuits, including series, parallel, and then kind of combination circuits. So the first thing to remember is hopefully you kind of have this in your mind, this recap we did at the end of the last video, where it talks about how to predict how the total voltage, for example, might relate in a series or in a parallel circuit. So, these rules, it's really tempting for students to just try to memorize them. And if you're trying to memorize them, you're probably going to end up disappointed because, for one thing, they end up being so similar to each other. Like, look at the series rule for voltage and compare that to the current rule for parallel. Those kind of follow the same pattern, but why? It's much more important for you to understand the why of how these rules work out, and we'll kind of explain those as we go through these examples, and hopefully that'll start to stick so you're not stuck just memorizing things. So just a quick recap reminder that the total voltage basically is going to be the sum of the individual voltages when we're in series. So if we wanted to write that in fancy math writing, we might say that V total is going to equal sigma Vn, where this sigma just means the sum of, and then n is whatever number of components. So if you have 3 resistors in series, you can just find the voltage across each of them, add them up, that gives you the total. By comparison, in parallel, the total voltage is just going to be equal to Vn. So whether you've got 1, 2, 3 components, what have you, each individual component in parallel is going to get the same voltage as each other, no matter how many you've got. If we compare that to current, so in current, our series circuits in current, there's only one pathway to flow, so we know that the total current is just the same through each component in that circuit. So I total is equal to IN. Whereas in parallel, the current's going to split up, and it's going to go through different pathways, so the total current would be equal to the sum of the individual currents, so through the individual pathways. Last one here is resistance, and so for resistance, our total resistance in series, again, is going to add up, so it's going to be a sum. So the total resistance is the sum of the individual resistances. And I know I just said that I don't want you to memorize formulas. My experience is that students can kind of come to grips with those first 5 that we looked at. And those first 5 do make intuitive sense. That, for example, as you add more resistors in series, that we're just making it more and more difficult to go through the circuit. And so the total resistance is just going to add up as we go. So the first 5 formulas seem to kind of work. But this last one, I will admit that this last formula is the one that students just kind of shake their heads at and wonder what the heck is going on. And so while you can do a derivation, and you can derive this formula from Ohm's law, and we're not going to go through that because I don't think you want to. But what I do want you to notice from it, the key point with this formula is that as we add components in parallel, as you add more resistors in parallel, as you provide more pathways for the circuit, for the current to flow through, then the total resistance goes down. That's the big takeaway message from this formula here, that hopefully you can see that as you give the electricity more options to flow through, the total resistance will decrease. I do want to point out there's another way to write this formula which might be more palatable for you, and certainly how we're going to put it in our calculator. We can write an inverse of something. So for example, 1 over RT, we can write that as RT to the negative 1. So if it simplifies things, you could think of this as just being R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1, and so on. So if that's like an easier way for you to do that, to write it, then feel free to do that. And again, that's how we're going to be punching it into our calculator. So for example, if I wanted to put 1 over 10, I could just go 1 divided by 10, and that would give me an answer. But I could also just put 10 and then use this to the negative 1 function, and then that will return the same answer. So that's just going to be a little bit quicker and easier for us to work with, and so that's what we're going to do. Okay, so let's just get into some examples here. So, there's a few just kind of tricks we're going to learn as we get practice with these. And the first is that, okay, we're going to identify what kind of circuit we're dealing with, because that's going to change the rules that we're allowed to use in each case. And so I've got this circuit, I've got a 12-volt battery plugged in, and you can see that as current's going to flow through here, there's only a single pathway for it to move in. So this is a series circuit, so I can only use my series rules. I know the total voltage provided by the battery. I know the resistances of each individual resistor, and what they're asking for is what's the value of I1, I2, and I3. So what's the current through resistor 1, resistor 2, and resistor 3? Well, the first thing to notice is that this is a series circuit. So I1 is going to equal I2, and that's going to equal I3. The current's going to be the same everywhere. And in fact, this current is going to be the same as the total current. So if I could find the total current, then I've actually figured out each of these individual currents because they all have to be the same. So the second sort of strategy I want you to think about once you know what circuit you're dealing with is that sometimes with these circuits you're not totally sure how how something is going to help you solve it, but you just want to go through, and if there's anything that you can figure out, go ahead and figure that out, and then it might be useful later. So for example, I've got R1, R2, and R3, so I know that I can find R total. So R total, since it's series, is just going to be the sum of the individual resistances. So that's just 3 plus 4 plus 2. And so this is going to add up to be 9 ohms, 9.0 ohms. So I know my total resistance. I want to find my total current. And as it turns out here, I know my total voltage because the total voltage is the voltage at the battery. So if I know total voltage, then I can use Ohm's law. V total equals I total times R total. And I can use this to solve for current. So I total will just be voltage total divided by resistance total. So that's going to be 12 volts divided by 9.0 ohms. And when I return this into my calculator, I get 1.3 amps. And now again, this is the answer because this is the current for all three of those points. So I want to bring you back to Ohm's law really quickly before we move on. I said V total equals I total times R total. You got to remember that Ohm's law is true for whatever part of the circuit you want to look at. It's true if you want to look at the whole circuit. It also would be true if you just want to look at individual components. If you just want to look at one resistor, then that's going to follow Ohm's law as well. And we'll see an example of that here in a sec. Okay, so what is the value of R2 in the circuit shown? So we've got, I know the voltage of my battery here. I know a current reading at an ammeter. And then I've got 3 resistors, and they are in parallel. So I'm going to have to use my parallel rules. Well, the other thing about solving these circuits is that there's often more than one way to do it. So I'm gonna show one solution, and I'm gonna kind of leave it for you to see if you can figure out there is a different way to actually solve this exact same problem and end up with the same answer. So I'm not sure what I'm gonna do here, but I notice here that I've got my total voltage, right? Because that's the voltage at the resistor, or sorry, at the circuit, at the battery. So that's my total voltage. And then I've got this ammeter placed right here, and this ammeter is going to be measuring total current. And it's going to be measuring total current because that's at a place before any of the junctions, before any of the splits had happened, right? And that's important to notice. If I put the ammeter here, for example, this would not give me the same reading as this one. They're not equivalent because this second ammeter would be in a place that's missing this whole junction right here. So just as it happens though, this ammeter is showing my total current. So if I know total voltage and I know total current, well, why don't I just go ahead and use Ohm's law to find the total resistance. So 24 volts divided by 1.80 amps gives me 13.3, and it's actually 13.3 repeater, as it turns out, ohms. I'm not worried about sig fig, so I'm just going to kind of hang on to that repeater sign there. Okay, so I've got the total resistance, but now what? Well, this is a parallel circuit, so I can use my rules for resistance in parallel, which is to say that the total resistance, the inverse of that to the negative 1, is equal to R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1. So I'm just looking for R2 because I know R1 and I know R3 and I know R total now because I just figured that out. So I'm just going to solve this for R2. I've got R2 to the negative 1 is going to equal R total to the negative 1, and I'm going to subtract R1 to the negative 1 and R3 to the negative 1. Now, I know all these like to the negative 1s can get a little bit confusing, and it's a little bit of an irritating notation, but just make sure we keep track of them. Note that that each of these has a little negative 1 associated with it. Like each of these is an inverse. I'm actually just going to just pause here a second, and I'm going to solve for R2 to the negative 1. So I'm going to put in values, and this might be a step early, but we'll just see what happens. So R total to negative 1, so that's 13.3 to negative 1 minus 40 to the negative 1 minus 60 to the negative 1. And let's just see what we get here. And I'm going to put this in my calculator here so you can see what I'm doing, because you want to make sure that it works out. So 13.3 to the negative 1 minus 40 to the negative 1 minus 60 to the negative 1. And then I get an answer. And this is the answer my calculator returns. It says 0.03352. 3352. Now, the reason I want to point this out is because a lot of students get to this point and they stop. And what I need you to recognize is that this is R2 to the negative 1. We haven't actually solved for R2 yet. And so I need to get rid of this little inverse that's still existing. So I'm going to put this whole thing to the negative 1, and I need to put this side to the negative 1 as well. So R2 is not 0.03352. I need to take the inverse of that. So the inverse of this number. And so I can just go second function answer and then take the inverse of this, and I get the answer of 29.8, which is right around 30 ohms. So I've got 30 ohms. And that is my answer for R2. Now, I just want to point out something real quickly here. When you're doing these calculations, it's really easy to lose track of what makes sense. You're just kind of punching numbers in your calculator and you're going, well, I don't know. Calculator says it's 30 ohms. I guess it's 30 ohms. And you're sort of at a bit of a loss. But I do want you to stop and think about that number and see if it makes sense. 30 seems like a reasonable number for a few reasons. For one thing, it's sort of in the neighborhood of these other resistances, but that's not necessarily the only thing. One thing about this number is that it is bigger than the total resistance. Remember, my total resistance here was 13.3 ohms, and the R2 value is 30 ohms. As you add resistors in parallel, it reduces the overall resistance. So it gets smaller and smaller. So there's no way this pathway here, this R2 pathway, there's no way this could have been lower resistance than the total 13.3. And the fact that it's around 30 kind of gives me a reasonable, I can be reasonably certain that, yeah, that makes sense. If this pathway is 40 and this one is 30 and this one is 60, overall the total resistance is going to be lower and it's going to be around 13.3. So at least it's it's in the ballpark and seems to make reasonable sense. Okay, we're going to look at another example here, and here it's going to get a little bit more complicated. So I told you the first thing you want to figure out is what kind of circuit you're dealing with. And the first thing you might notice when you look at this is we don't know what kind of circuit we've got, because while this resistor is in series with this resistor, R1 is in series with R2, R1 is also in series with R3, but R2 is in parallel with R3. And so what we've got here is kind of a combination, kind of got a combo circuit happening. One of the strategies you can kind of use that I find kind of useful is to take this whole chunk of the circuit right here, take this parallel chunk of the circuit, and just imagine that it is one single component. So I'm just going to redraw my circuit here where I've got resistor here, R1, and then I'm going to think of that whole parallel chunk as being just a single thing. So here's R1, and this is 8 ohms. That hasn't changed. But I'm going to think of this whole thing as just being one component. I'm just going to call that RP for R parallel. You can call it whatever you like. I know my current here is still 2 amps. Now what's going to make this kind of tricky is because this is a kind of a combination circuit of both parallel and series resistors, we're going to have to use both rules at different times. So for example here, these components here are in parallel with each other. So I could figure out the resistance of that component by using my parallel rules. So I could say that Rp to the negative 1 is equal to R2 to the negative 1 plus R3 to the negative 1. So subbing in my values here. Now actually, maybe I'll point out at this point right here that this little negative 1, I can get rid of it early on. I didn't do it in that last example, but I could rewrite this as Rp is equal to, bracket, R2 to the negative 1 plus R3 to the negative 1, all to the negative 1. And so then when I substitute my values, I get 12 to the negative 1 plus 24 to the negative 1, all to the negative 1. Now, before you put this in your calculator, this is what I was saying before. Before you just hammer these numbers in and believe whatever it tells you, have an idea of what your answer could be here. We know that as we add more pathways in parallel, the total resistance has to go down. So I know my total resistance of the parallel pathway has to be less than 12, for example. So let's see what we get when we put that in. So 12, I forgot my bracket, 12 to the negative 1 plus 24 to the negative 1, and then all of this to the negative 1 gives me 8. Now, based on what we said before, 8 is a reasonable answer. It's less than 12. It's not way less than 12. Because this second pathway has a resistance of 24. And so we can be reasonably confident we've got the right answer there. Okay. So I now know the resistance of this pathway here, which is 8 ohms. So not totally sure if this is going to be helpful or not, but why don't I just go ahead and figure out the total resistance of the circuit, because the total resistance of the circuit will be R1 plus RP. Remember here that R1 is in series with RP, so we're going to use our series rules, whereas R2 and R3 were in parallel, so before we had to use our parallel rules. So this is going to be 8 plus 8, or 16 ohms. So I now know my total resistance, and let's see what else I can figure out here. Well, this current right here up at this point, the current that was given to me, this current really is the total current, because it's going to measure the current that's just going through the battery after it's gone through the other components in the circuit. So that is the total current. And what is the potential difference supplied by the power source? Potential difference is just fancy talk for voltage. So really what we're looking for is what is the total voltage provided by the battery. I know total resistance, I know total current, so that I can now find total voltage. So V total is simply I total times R total, which is 2 amps times 16 ohms, which gives me 32 volts. And that's my final answer. Okay, we're going to do one last example here. We'll see how this goes. All right, so we've got another circuit here, and you can see this is starting to get a little more complex. There's more components. There's 4 resistors. There's different things that I know here. I'm looking for several things. So I'm looking for V1, V2, R2 in this circuit. So I'm just going to kind of draw those in so I make sure I know what I'm looking for. So I'm looking for the voltage here. So I want to know, what is the voltage across this resistor? What is the voltage here across this resistor? What is the, where are we? And what is R2? What is the resistance of that resistor? Now, what do I know? Well, I know most of the resistances except for R2. I know the voltage of the power supply here, so I know the total voltage for the circuit. And then I only know the current right here. I only know current through this resistor R4. So this is a great example where there's a whole bunch of things I need to figure out. V1, V2, R2. And I might have no idea where to start. I might be completely at a loss, but you can just find out something. So if there's anything you can find out in this circuit, just go ahead and find it, because who knows where it might lead. The more you can learn about this circuit, the closer you'll get to the answers you're looking for. So, for example, when I say if you can find anything, what I mean is if you think about Ohm's law, there's only voltage, current, and resistance. If you ever know any two of those things, just go ahead and find the missing thing. And let's see what that tells us. So like, for example, I know here the current and the resistance of this pathway. So I'm going to use that to find V4. So V4 would just be I4R4. So what is it? 0.3 amps times 20 ohms. So this is going to be 6 volts. Okay, awesome. But how does that even help me? The voltage across this one resistor here is 6 volts. Well, as it turns out, if the voltage across this resistor is 6 volts, and these two resistors are in parallel with each other, then the voltage across this resistor also has to be 6 volts. They have to get the same amount of energy because they're in parallel with each other. So if I know V3 and I know R3, well, then I'm just going to go ahead and find the current, I3. So I3 would just equal V3 divided by R3, which is 6 volts divided by 30 ohms, which is 0.2. Okay, so that's great. So I now know, I'll just fill this in here, I3 is 0.20 amps. Okay, well, if I know the current through this pathway, I know that 0.2 amps is flowing through here, and I know that 0.3 amps is flowing through there, then I guess I could figure the total current that flowed into those two pathways. And that would be the same as the total current that flows out of those two pathways. So essentially, I could find the total current because they split up and go through those two spots, but they must have been, they must add up to the total to start with. So I total must just equal I3 plus I4. And so that's 0.2 plus 0.3, so 0.5 amps. So I've got half an amp going through my circuit. And you can see here like how important it is to kind of keep things organized. And you can't just talk about voltage and current. You need to talk about voltage 1 or current or I3 or whatever it is. You need to keep things nicely organized. So I now know the total current through my circuit. Well, these two resistors, V1 and V2, these two resistors are in series with everything else. So if the total current is 0.5 amps, then that must be the current here. So I1 must also be 0.5 amps, and I2 must be 0.5 amps. And now we're getting pretty close to it because you can see I can actually finally solve one of the things that I was originally supposed to try and find, which is I can actually figure out what V1 is because I know I1 and I know R1. So let's find V1. V1 must just be I1 R1. So the current of 0.5 amps times the resistance of 18 ohms. So this is 9 volts. So that's actually one of the answers I was looking for from the beginning. This is 9 volts right here. And now all I've got left is I've just got to figure out everything else about resistor 2. So I need to find the resistance and the voltage on resistor 2. Well, I know one more thing about my circuit that's going to be really useful. I know the total voltage. I've kind of ignored that up until now. So I know the total voltage. I know the voltage used across R1. And I know the voltage used across R3 and R4. I just need to figure out the voltage used across R2. Now here's where things get a little bit tricky. We've got 60 volts total. You know you're going to spend 9 volts on resistor 1, and you're going to spend 6 volts on either resistor 3 or resistor 4. but you're not going to spend it on both of them because those are in parallel. So again, if you think of this component here as being one parallel circuit, I could say, I could look at my total voltage and say that total voltage is going to equal V1 plus V2 plus V parallel, not plus VPN plus V3 and V4, because I only need to use the voltage on one pathway or the other. So essentially the V2 is just going to be the difference. So take my total, subtract what I use at V1, subtract what I use at the parallel component, and that's it. So 60 minus 9 minus 6 gives me 45 volts. So I must have 45 volts. And by the way, that's one of the answers we're looking for. So I'm just going to box it out. So I must use 45 volts here. Now, all we have to do is figure out, last step is to figure out now the resistance of this pathway. And you can see I know the voltage and the current. So I'm going to find the resistance. So R2 is just going to equal V2 divided by I2, which is 45 volts divided by 0.5 amps, which gives me a resistance of 90 ohms. Which sort of makes sense because I use most of my voltage here on this resistor, so it makes sense that this resistor has the highest individual resistance. So those numbers seem to work. Okay, that's it for the little tutorial on using Kirchhoff's laws.